All right, who's ready to start the application section? 5.6 is really just about the applications and models of exponential functions, okay? Now, when we're dealing with exponential functions, we may have to use logs to change it from an exponential equation to a logarithmic equation if the unknown that we're solving for is up in the exponent. So it's the same type of solving techniques that we went over in 5.5, but just applied to a word problem. Okay, so in 5.6, we're going to use this, this formula right here. P of t equals P naught, or P sub 0. We refer to that as P naught, e to the k times t. Okay, now k is our rate. It's our growth constant or it's our decay constant. So when we talk about decay, our k will end up, or when we talk about decay, our k will end up negative because over time it's decaying, which means that there should be less amount of whatever it is that we're talking about, right? Growth over time, there should be more. So our rate should be a positive one. Okay, we're not going to get into graphing them, but I did graph each of them just so that you're reminded. This is just an e to the x exponential function, right, that will have been adjusted because of whatever our p naught value is and our time value. Same thing here. If it's a decay, it looks something like this. Okay, we're not going to graph them, but I do want to make sure that you know how to use these. So whether we're dealing with growth, decay, continuous compounding, all of it is going to use the exact same formula. And I will give you this formula on the formula sheet or on your exam, but you have to know what all the little pieces of that formula represent. Okay, so I'm going to come down here and just write it down at the bottom. So if we have P of t is equal to P sub 0 e to the kt. Our P of t value, this whole side of the equation, represents our end amount. So how much do we want to end up with? Or if they say, you know, from this year to this year, I went from this to this, it would be our ending amount. Okay. P naught or P sub 0 is our beginning amount. Okay. Our initial investment or our initial volume or our initial population, whatever we started with. Okay. K is our rate, and we always write it in our function as a decimal. Okay, so if it's given as a percentage, make sure when you write it into our function or when you're evaluating that you write it as a decimal. Okay, and then T is our time, usually in years. Okay, so basically what they're going to do is they're going to give us something, we have to solve for what they didn't give us. So they might ask us what the end amount would be given a certain time. Well, if you need to know the end amount, then you should know the beginning amount, you should know the rate, and you should know the time so that you can solve for this, right? Or if they ask you to find the beginning amount, you should know the end amount, you should know the rate, and you should know the time. Okay, or if you're solving for one of these two up in the exponent, right, you should know the beginning amount and the ending amount and whichever one they didn't give you. So you're basically solving for what's not given. Okay, one little special note that I would like to make here is that you always keep at least 4 decimal places for K. So when you're dealing with the rate, you always want to keep at least 4 decimal places. The reason is this rate needs to be very specific so that when we multiply this out, we're getting the most accurate answer. So a lot of times in my math lab, they may have you enter at least 4 or 6 decimal places sometimes. Most of the time it's 4. But let's say you get K equals 0.3219, something like that. A lot of times they'll let you leave it as 4 decimal places, or they'll have you write it as a percentage. And so if we move our decimal place 2 places, this would be 32.19%. And when we write it as a percent, sometimes they'll have you keep at least 2 decimal places. So keeping 4 to begin with will ensure that you have enough if you have to write it as a rate. Okay, so just a heads up on that. Always keep a lot of decimal places when you're dealing with your rate. Okay. All right, so let's just jump into some examples. So for these examples, we're going to round our k to 4 decimal places if we have to solve for k. Sometimes the rate's given and we don't have to solve for it, okay? All other answers, we're going to round to the nearest whole number, okay? All right, so it says population growth of Ghana. In 2014, the population of Ghana, located on the west coast of Africa, was about 28.5 million, and the exponential growth rate was 2.9% per year. Okay, so the first thing it wants us to do is find the growth function. So the growth function is that formula I just showed you, P of t equals P sub 0 e to the kt, or you may have learned this as APERT, right? For those of you who've seen this before. This is just written in function notation. Okay, so in order to write this function, we know we want to call it P of t, but we need to know our beginning amount and we need to know our rate in order to write this equation. So for part A, we want to write P of t is equal to P naught e to the kt, but we need to know our beginning amount and we need to know our rate in order to be able to write this function. So our beginning amount, or our starting population, when we're talking about Ghana in 2014, it says our population was about 28.5 million. So that's going to be our starting value, or our initial amount, okay? And then it tells us the growth rate is 2.19%. Now, when we take our percentage and we write it in our function, we want to make sure we write this as a decimal. So remember, to move it to a decimal, we would go back 2 places. So this would be 0.0219 as a decimal. Okay, so taking all of that, we should now be able to write this as our function. The population at time t is equal to our initial population, which we know is 28.5 times e raised to the k, which is our rate, so 0.0219 times our time, which is t. Okay, so when we're just writing the growth rate function, we shouldn't have values in for t, because this is telling us the population at time t can be determined using this formula. Okay? All right, so that was the first thing. So now that we have the function, now we could do several things, right? Now that we have the function, we could find the ending amount by just plugging in, whatever time, or we could find the time if we're given an end amount, right? So let's see what part B wants us to do. For part B, so this is all part A. All right, so for part B, it says estimate the population in 2018. So in 2018, I need to know what t to plug in. Now I don't want to plug in 2018 because that's not telling me years. That's telling me the actual date, right? So notice my formula has a beginning amount of 28.5, which was the population in 2014. So I need to know how many years since 2014 has gone by. And we can see here that that's 4 years. So we're going to plug t equals 4 into our function. So here's our function. So we have the population after 4 years is going to look like 28.5 e to the 0.0219 times 4. And now we just have to simplify this side. So order of operation tells us to do our exponent first. So this gives us 28.5 times e to the, when I multiply 0.029 and 4, I should get 0.0876. And now I need to go ahead and raise e to that power. So I still have my 28.5 times, when I do e raised to the 0.0876, I get 1.09155 and some more stuff. Okay, I'm not going to write it all out, but make sure you leave all the decimal places in your calculator till the very end. Then I multiply these two numbers together, which gives me 31.10921 and some more stuff, right? So this is what I'm ending up for my population in 2018. So this is representing my population. Notice here my population is in millions. and we're just going to go ahead and round it to the nearest whole number. So we're going to say this is approximately 31 million people living in Ghana by 2018. Okay? All right, so now let's look at part C. So this was all part B. So now part C says, at this growth rate, when will the population be 40 million? So we want to know when. When it says when, we're looking for a calendar year. Okay, so it wants to know, like, will that happen in the year 2042? Okay, we're not just looking for t. Now, we are going to have to use t to find the time, but once we get t, remember that tells us the number of years, and then we would have to add those years to our starting year to figure out how far in the future when this is going to happen. Okay, so when will the population be 40 million? So 40 is going to be our end amount. Okay, so we're going to use our same function, but instead of plugging in a time, we're going to plug in what we want it to equal, which is 40 million. So we have 40 million is equal to our 28.5 e to the 0.0219 times t, and we're solving for t. So what time is this going to happen? Well, t is stuck in the exponent of the e, right? So I need to get the e isolated first. So I'm going to go ahead and divide off my 28.5. So on the left side, 40 divided by 28.5 is going to give me 1.40 and some more decimal places is equal to, on the other side, I'm left with e to the 0.029t. Okay, and now that I have e isolated, I can go ahead and get rid of it by taking a log so that I can either bring this down, or in this case, because it's an e, I can just use ln, so it will cancel out that e. But if I do ln on one side, I have to make sure that I do ln on the other side. Okay, that way my ln and my e will cancel. Once those happen, I can do ln of 1.40 and some more stuff is now equal to just 0.0219t. And then to get t by itself, all I have to do is divide off the 0.0219. So I end up with t is equal to, I'm going to, in my calculator, do ln of this value. Now remember, we want to leave all of our decimal places till the very end. So don't round this, okay? Remember, this number came from doing 40 divided by 28.5. That's how we got this decimal, okay? And then we want to take ln of that decimal, whatever that equals, and we're going to divide it by 0.0219. And that should give us 15.478 and some more stuff. And remember, t, we're looking for time, so this is talking about the number of years. So we're going to say t is approximately 15 years, okay? Now, 15 years is telling us how long it took, but it didn't ask how long, it asked when. And when means we want the calendar year. So remember, our function started in 2014, and we just figured out that our time is 15 years for it to reach 40,000. So I'm just going to add that. So that means that the population in Ghana will reach 40 million by the year 2029. Okay. Are we kind of okay? Kind of okay. All right. Oh my gosh. So that was part C. So on this particular problem, they gave us the rate. So that was kind of the nice version, is when they give us the rate and the starting amount, so we can right away come up with our function. And then once we have our function, they either give us a t to plug in, like we did on part B, or they give us an ending amount to set it equal to, like they did on part C. What we're going to look at now is problems where they don't give us that starting rate. So if they don't give us the rate, we have to solve for the rate first so that we can write our function. Because if we don't have our function, we can't solve for anything, right? So we're going to go ahead and figure out the rate first so we can write the function. And once we have the function, then we can either plug something into it or set it equal to something. Okay, so let's go ahead and look at the one on the top of page 52. Excuse me. All right, so this one is talking about interest compounded continuously. So we're not talking about simple interest. We're talking about compounded continuously interest, which is a dead giveaway that we're going to be using, again, this equation. Now, usually we use P when we talk about population. When we talk about money, sometimes they'll use an A because they're talking about the amount. So if you see this written as A of t equals A naught e to the kt, it's the same thing. It's the same formula, just sometimes they use A's instead of P's, right? Or sometimes they'll even write it without the function notation. They'll just say A equals PE to the RT. All of these are exactly the same. Whatever's on the left-hand side is your ending amount. Whatever is the constant after the equal term is your initial amount. And then K is your rate. In this case, if you write it as an R, that's your rate. And T is your time. Okay. So again, these formulas will be given to you on a test and for the final. You just have to know what each of the little letters stand for based on where they're at in the formula. Okay. All right. So this one says, suppose that 2,000 is invested at an interest rate K, compounded continuously, and grows to $2,504.65 in 5 years. Okay, it says note P naught would be the principal and K would be the interest rate. So we're going to go ahead and just use our normal function. Okay, I don't care if you ever write it like this. I just wanted to put that up there in case my math lab throws something at you like that, that it's all the same thing. A says, what is the interest rate? So what we don't know is our K. So if we don't know our K, here we have P of t is equal to P naught e to the kt. So if we need to know K, that's what we're solving for, then that means we should know our ending amount, we should know our beginning amount, and we should know our time. Okay, because that's everything else we need to know in order for this to work out. So this one says, suppose that 2,000 is invested. If 2,000 is what we invested, that's our beginning amount. So our beginning amount is 2,000 and it grows to 2,500, right? That's going to be our ending amount, is the 2,504.65. And it says it grew from 2,000 to this amount in 5 years. So that's going to be our time. So now that I've figured out what everything is other than K, I can plug all these values in so that I can solve for K, right? So let's go ahead and plug those in. So my ending amount is 2,504.65, and that's equal to my initial amount, which was 2,000, times e raised to the k, which we don't know, times t, which we know to be 5. And now we're just solving for that rate. Okay, so when we solve for that rate, it is stuck in the exponent of the e. So we need to get the e isolated. So we're going to start by dividing off the 2,000. So we divide by 2,000. This is going to give us 1.252325 is equal to e to the 5k. It doesn't matter if you write it as k times 5 or 5 times k. I'm going to write it like this just so I don't have to keep putting parentheses. Okay. And now that my e is isolated, I can get rid of it using the ln. So I'm going to take the ln of 1.252325, and on the right-hand side, the ln of e to the 5k. So my ln and my e will cancel, and I'm left with ln of 1.252325 is equal to 5k. And then the last thing I have to do to get k by itself is divide by 5. So that means that k is equal to 0.045000, a whole bunch of stuff. Okay, now remember, k is our constant. This is the thing we need to be specifically and super duper accurate. So we're going to keep 4 decimal places. So if I count to 4 decimal places, oops, sorry. If I count to 4 decimal places, that is the 0 behind the 5. And since there's a 0 behind it, it doesn't bump it up. So we're going to go ahead and say k is approximately 0.045. Okay, so that is our interest rate. Now, that is our k. So if we want to know what it is as a rate or as a percentage, we would just move it 2 places to the right. So this would be 4.5% as an interest rate. Okay, but when we write it in our function, make sure you leave it as a decimal. Okay, so that's what part B is now asking us to do. Find the exponential growth function. So now that we have our beginning amount and we have our growth rate, we should be able to put this in function form. So again, I'm just going to write what our function looks like and then put in my specific values. So we know our starting principal amount was $2,000. And now we know our rate, which we're going to write as a decimal. So 0.045 times t. So now we have our growth rate function. Okay. So unlike the last one, we first had to solve for our rate. Now that we know our rate, now we have our function. And once we have our function, now we can either set it equal to something or we can plug in a time. So let's see what part C wants us to do. So for part C, it wants us to evaluate what will the balance be after 10 years. So they're giving us 10 years, so that means t equals 10. So we're just plugging in 10 for t in our function. So our principal after 10 years is going to look like 2,000 e to the 0.045 times 10. Order of operations says to do our exponent first. So this is equal to 2,000 times e to the 0.45 when I multiply those exponents together. Then I go ahead and do e raised to that power. So I have 2,000 times e to the 0.45 is 1.568 blah, 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 and some more stuff. And then I go ahead and multiply that by the 2,000, which gives us 3136.624 and some more stuff. Okay, and remember, we're looking for the balance. We're talking about money. What was the balance after 10 years? So normally we round to the nearest whole number, right? Because that's what our instructions said. But if you look back up at this problem, when they were talking about money, they actually gave cents. So I'm going to go ahead and leave 2 decimal places for cents here. So we're going to round it there, which is going to be approximately $3,136.63. Okay. And then part D, the last piece of the puzzle here. Part D says, how long will the 2,000 have doubled? That doesn't make any sense. How long will it take the 2,000 to double? This is a really bad way to word this. Basically, we want to know the doubling time. So after how long will the 2,000 have doubled? So for it to double, that means that our ending amount would be 4,000, right? So our ending amount, remember, is this side of our function. So we're just going to set it equal to 4,000. So we have 4,000 is equal to our initial amount, which is 2,000, times e raised to our rate, which is 0.045 times our time. And we're looking for the time it takes for this to happen. So we need to get the e by itself first. So we're going to go ahead and divide off the 2,000. We divide off the 2,000. That gives me 2 is equal to e to the 0.045 t. And then we take the ln of both sides so we can get rid of that e. So ln of 2 is equal to ln of e to the 0.045 t. So my e and my ln cancel. And we're left with ln of 2 is equal to 0.045 t. And then to get the t by itself, we just divide off the 0.45. I'm out of room here. So this means that t is equal to, if I do ln of 2 on my calculator and then divide it by 0.045, I should end up with 15.403 and some more stuff. So again, I want to make sure it wants to know the number of years and not a date. So when I go back up here, it says after how long. So how long means we just want to know the years. Okay, if it wants to know a year, like an actual calendar year, it would say when. Okay, but since it says how long, we just want to know the number of years. And if I round it to the nearest whole number, this means it's approximately 15 years. Okay? All right, so I want to look at one that basically does the exact same thing we did here. One where we have to first find the interest rate so that we can come up with our growth function or decay function. Okay, and then once we have our function, then we can either plug something into it or set it equal to something. Now, this one was kind of nice because we were dealing with money. So it's really easy to see we're beginning with this amount, we're ending with this amount, because these are normal, just whole number amounts. The next example, we're doing the same type of thing, except the amounts are actually percentage amounts. Okay, but we're going to work it the same way. So we're still dealing with P of t is equal to P naught e to the kt. So let's look at our carbon dating problem. It says the radioactive element carbon-14 has a half-life of 5750 years, or 5,750 years. The percentage of carbon-14 present in the remains of organic matter can be used to determine the age of that organic matter. Archaeologists discovered that the linen wrapping from one of the Dead Sea Scrolls had lost 22.3% of its carbon-14 at the time it was found. How old was the linen wrapping? Holy moly. It says, hint, first you need to determine the value of K. So notice it didn't give us a rate, a percentage rate. The only percentage it gave us was 22.3%. But that's not saying it was decaying at this rate. What it said is that we can find the amount of carbon to determine the age, right? So everybody starts with 100% of their carbon, right? Everything on Earth that we could test its carbon amount, right? It starts with 100%, and then as it decays, the percentage goes down. So what it's talking about, this wrapping from one of these scrolls, it had lost 22.3% of its carbon. That's talking about the amount. So we're going to use that when we start thinking about our beginning amount or our end amount, but it's not giving us a rate. So we first have to find the rate. So I'm going to say, whoops, we need to find K. Now, in order to find K, right, we need to know everything else. So we need to know the end amount, we need to know the beginning amount, and we need to know the time that it took to go from that end amount to the beginning amount. So we've talked about carbon-14. Everything starts with 100% of its carbon. So beginning, we should all start with 100%. And then the end amount is what it has decayed down to, what percentage we're currently at. So to get this information, I'm going to use just this first sentence that says the radioactive element carbon-14 has a half-life of 5750 years. A half-life means that it's gone down to 50% of whatever it started with. So if we start with 100% and we're at the half-life, that means we're down by half. We're at the 50% mark. So that means we're ending with 50% of the carbon we started with. Okay? And how long that takes us is how long the half-life is, which is 5,750 years. So just this one sentence at the beginning is enough information for me to be able to go ahead and solve for K. So I'm going to go ahead and put in my function P of t is equal to P naught e to the kt. I'm going to put in my ending amount, which is 100%. No, it's not. I'm lying. Don't listen to me. We're ending with 50%, right? Because it's a half-life. We're ending with half of what we started with. and that's equal to how much we started with, which is 100%, times e raised to our rate, which we don't know, times the time it took to go from 100% down to 50%, which is 5,750 years. Okay, now we don't like dealing with percentages. We like to make them into decimals. So before I start solving, I'm going to go ahead and convert these percentages to decimals. 50% is 0.5, 100% is 1, right? 1 times e to the 5750k. Now, 1 times anything is still just e to the whatever, right? So I'm going to go ahead and just rewrite this without that 1 there. And now we can go ahead and take the ln of both sides to get rid of that e. So ln of 0.5 is equal to ln of e to the 5750k. ln and e are going to cancel. So I'm left with ln of 0.5 is equal to 5750k. And then to get k by itself, we just divide off the 5750. Okay. So that tells us that k is equal to, now ln of 0.5 divided by 5750 is going to give us negative 0.000120 and some more stuff. Okay. Now remember, k is the thing we need to be super accurate, so we're going to keep 4 decimal places. So if I count this over to 4 decimal places, 1, 2, 3, 4, that's our 1. There's a 2 behind it, so we're going to go ahead and just approximate k to be negative 0.0001. So now that we know what k is, we should be able to come up with our function, right? Because our function is equal to our starting amount times e raised to our rate, which we now know, times t. So our function, p of t equals p naught e to the kt. We have p of t is equal to, now remember, our beginning amount is 100%, right? So if I write 100% as a decimal, that's just 1, right? So I'm not even going to write it. I mean, well, I guess we can write it. 1 times e to the k, which we just found to be negative 0.0001 times our t. Okay. All right. So this is our growth rate function. So now that we have found our growth rate function, we should be able to evaluate. Either we can be given a time and we can plug it in and tell whoever how much carbon-14 is left over, or if we know how much carbon-14 is left over, we can figure out the time. Okay, so let's look and see what they want us to find. Now let's go back up here because we only use the first sentence. Second sentence, the percentage of carbon-14 present in the remains of organic matter can be used to determine the age of that organic matter. Okay, that's just information. Archaeologists discovered that the linen wrapping from one of the Dead Sea Scrolls had lost 22.3% of its carbon-14 at the time it was found. How old was the linen wrapping? Okay. All right. So we know how much carbon it lost, and we're looking for how old it is. So if we're looking for how old, that means we're looking for time. We want to know how much time has passed, right? Since we found this linen wrapping. That tells us the time. So if we know the time, that means that the only thing we don't know, or the thing we should know, right, if we're solving for time, is the end amount. So our end amount is how much carbon-14 is present, okay? Now it doesn't tell us how much carbon-14 was present. It tells us how much carbon it lost. So if it lost 22.3%, that means it's down from its original 100%, it's down 22.3%. So I'm going to go ahead and just say we started with 100%. We lost 22.3%, which means we are now at 77.7%, right? All right, so this is our end amount. So I'm going to go ahead and use this function that we came up with, and I'm going to put in 77.7% as our end amount. So 77.7% is our end amount, right? Down from the 100% we started with. And we have e to the negative 0.0001 times t. And then again, I'm going to go ahead and take this out of percentage and write them as decimals. So if I move this 2 decimal places, this becomes 0.777 is equal to 100%. Remember, as a decimal is just 1. So I'm not going to write it because 1 times e to the whatever is still just e to the whatever. So this just becomes e to the negative 0.1230, a 1, and t. And now I should be able to solve this because I can get rid of the e by taking the ln of both sides. So ln of 0.777 is equal to ln of e to the 0.0001t. Sorry, negative. And my ln and my e cancel. So that leaves me with ln of 0.777 is equal to negative 0.0001t. And then I can divide off that coefficient. Divide by negative 0.0001. So that tells me that t is equal to, if I do ln of 0.777 on my calculator, I should get a negative number. And then when I divide that by negative 0.0001, it should come out to be 2,523.149 and some more stuff. Okay. So remember, we were wondering how old this linen wrapping is, which means we're solving for time, which is the number of years. So we're just going to round to the nearest year here and say that it takes about 2,523 years for that carbon-14 to have decayed from 100% down to 77.7%, which means that that's about how old the linen wrapping of this Dead Sea Scroll actually is. Okay? All right, so on the next 3 pages, there are 3 for y'all to try. If you get stuck, and need help, go ahead and unpause it and I'll talk through them. Otherwise, go ahead and work through it and then unpause the video when you're ready to check yourself. Okay. All right, so on the first one, we're talking about the population growth of a town in North Carolina, right? We know our starting population was 438,000, and this one, the rate was given to us, 0.034. So if we know the start rate and we know the rate, the starting amount and we know the rate, then all we have to do is plug it in and we should have our formula. Okay, make sure you write your rate of 3.4%. Make sure you write it as a decimal when you put it in your function. Okay. Part B is asking us to estimate the population in 2019. So 2019, we first have to figure out how many years it's been so that we know what t value to plug in. So 2019, subtract our starting year, which was 2014, and we can see that 5 years has passed. So 5 years is what we're going to plug in to our function. So we just take our function we just came up with in part A, and we're plugging in 5 everywhere we see a t. So simplify your exponent first, then raise e to that power, and then multiply that by your 438,000, and we should get a population of approximately 519,164. Okay? All right. For part C, it says, when will the population area of this metropolitan area be 500,000? Okay? 500,000 is what we want the population to be, or our end amount. Okay? So I'm going to take this function, and this time I'm going to plug 500,000 in over here for the end amount. So that gives me 500,000 is equal to our initial population of 438,000 times e to our rate, which is 0.034t. Then I had to get e by itself, so we divide off our starting amount, which gives us a decimal. Then I take ln of both sides to get rid of the e, and then I can divide off that 0.034 that's attached to the t. Okay, so when I do that, I solve for t, that gives me 3.89 right? Now you can round here, you could round the t up to 4, or you can go ahead and take that t and add it back to the year and then round. Either way is totally fine. I actually probably should have done it the other way. I would round my t to 4 here. So say it takes about 4 years for it to reach 500,000. But notice it's not asking me for the number of years. In part C it says when. When will the population hit 500,000? So it's saying when, it's asking for what calendar year. So once you know your t is about 4 years, you add 4 back to your starting year of 2014, which should be 2018 being the year that it would hit 500,000. Okay. And then part D is the same type of problem, except instead of them telling you the ending population, they're just saying find the doubling time. So that's where your population doubles from whatever it was initially. So we just take our starting population of 438,000 and double that, which gives us 867,000, and then set it equal to our function. Okay, again, divide off our initial amount, take the ln on both sides, and then divide off the coefficient of the t. So our time should be about 20 years. Okay? All right, let's look at the second one, which is talking about ebook sales. Now this is one where we're going to have to come up with the rate, and it's also one where our amounts are given as percentages. Okay, so this one says the revenue from ebook sales accounted for only 5% of U.S. publishing sales in 2006. And then that percentage grew to 22.6 in 2012. So notice this is my starting amount. We're talking about the amount is percentage of sales. So it went from 0.5% up to 22.6%. So that's my start and my end values. And the time it took to do that, well, that was from 2006 to 2012. So if I subtract those years, that means that it took 6 years for it to go from 0.5% up to 22.6%. So if I have a start, an end, and a time, I have enough information to solve for K. So I'm going to put my end percentage in and make sure you write it as a decimal. So 0.226 is equal to my initial percentage, which was 0.5. So as a decimal, that would be 0.005 times e raised to the k, which we don't know the rate, times the time it took, which was 6 years. Okay. Then again, we want to get e by itself, so we divide off that initial rate, and then we take ln of both sides to get rid of that e, and then we can divide off the 6 that's attached to the k. So notice if we're solving for k, we want it to be super accurate, so make sure you're saving at least 4 decimal places. So in this case, k would be about 0.6352. And now that we know our k, we can go ahead and write our function. So that means that our population function at time t should look like our initial percentage as a decimal, which is 0.005, times e raised to our rate, which is 0.6352 times our time. And now that we have our function, we can go ahead and either plug something in for t, or we can set it equal to something. In this case, for part B, it wants us to figure out the percentage of publishing sales for 2009 and for 2010. So it wants us to find 2 answers, and it says round to the nearest 10th. So first thing we're going to do in 2009, that means that 3 years has passed since 2006, right? So our time is 3. So we're just going to plug 3 into our function for t. And then whenever we work it out, remember, this is giving us the percentage of U.S. publishing sales. So if we ended up with when we work all this out, we get 0.033617 and some more stuff. And it wants to know the percentage at that given year, right? So I'm going to go ahead and move the decimal back over 2 places to get 3.3617. And then it says round to the nearest 10th. Notice I'm not rounding until after I've changed it back to a percentage, because this specific problem is talking about the percentage of sales in the US, okay? If it wasn't talking about a percentage, then I would have just left it as this original decimal, okay? Okay. And then we do the same thing for 2010. In 2010, 4 years have passed since 2006, so we're plugging 4 in for t. When we plug 4 in for t and simplify, we end up with 0.063 blah, blah, blah. And then we want to change it back to a percentage, right? So we move it 2 decimal places to the right, which means that the sales of ebooks in U.S. publishing would be about 6.3% by 2010. Okay? All right, and then the last one we looked at is our present value. So this is talking about a child being born and parents wanting to put an initial investment into a bank so that it will grow to $50,000 by the time the kid's ready to go to college, right? And they want to know, how much do we need to put in so that this happens? So our ending amount is we want to end up with $50,000 for this kid's college fund, right? And then the time that we're given is 18 years. The kid was just born and we hope to have this money by the time they're 18. And the rate is, it says it's compounded continuously at 7%. So our rate would be 0.07. So the thing that we don't know is how much money we need to invest to make this happen. Okay, so we go ahead and plug in everything that we know. Remember, this is our ending amount. So the 50,000 goes on the left-hand side, and we're solving for that initial investment. So again, we go ahead and simplify exponents, which gives us e to this, and then that's something we can calculate in our calculator, which is an ugly number, right? But it's still just an ugly number times our initial amount. Since we're solving for that initial amount, we can just divide off the ugly number. So when we divide it off, we get a nice decimal. And in this case, let's see, they didn't give us cent amounts in this one. They just gave us 50,000. So I just went ahead and rounded it to the nearest dollar. Make sure you pay attention to your instructions in my math lab, because it may say round to the nearest cent, round to the nearest thousand, round to the nearest $100, whatever. Okay. So I rounded to the nearest dollar, which means that the day that this kid is born, they need to put $14,183 into this account so that by the time the kid is 18, it will have grown to $50,000. Okay. All right. So that is the end of Unit 5. So you should now be able to complete Section 5.6 in your My Math Lab assignments. And once you're done with that, start working on the review at the end of the notes section to get ready for your Unit 6 test. Okay? If you have any questions, please let me know.